Welcome to Tech Trends. Tech Trends is a podcast series that provides perspective on the latest trends in technology, fintech, and digital. On today's episode, we're going to talk about quantum computing, what it is, how it works, and how it's changing the way we think about computing power, security, and the way we conduct business every day, not just in financial services, but in nearly every industry. I'm Anish Bhimani, Chief Information Officer for Commercial Banking, and back with us again is Marco Pistoia, Director of the Future Lab for Applied Research and Engineering, or FLAIR, at JPMorgan Chase & Company. Marco, welcome back to Tech Trends.
Thank you very much, Anish. Thank you for having me.
So Marco, we had you on a number of months ago to talk about 5G, a topic that was of great interest to all of our listeners. But you're also well known as an expert in the field of quantum computing, and I know it's an area of interest of research for you at FLAIR. For those of our listeners that are not familiar with the topic or haven't seen previous episodes, can you describe what quantum computing is and how it works?
Absolutely, Anish. I'll be happy to give an overview of quantum computing, which is actually a new form of computing, a disruptive form of computing that lends itself to problems with high complexity, problems for which classical computers have reached the limit. They cannot solve them unless they resort to approximations. And to signify the difference between classical computers and quantum computers, I think we should start from the basic units of computation. On a classical computer, the basic unit of computation is a classical bit. Everybody knows that a bit can be either 0 or 1. But in a quantum computer, the basic unit of computation is a quantum bit or a qubit. And a qubit can be 0 or 1, just like a classical bit, but it can also be any value between 0 and 1, literally 0 and 1 at the same time. And this is what gives a quantum computer such a strong power. This phenomenon is called superposition, and it is taken from quantum mechanics. And there is another phenomenon coming from quantum mechanics that is also at the foundation of quantum computing, and this is called entanglement. Entanglement is a principle of quantum mechanics that establishes that two or more particles can be in an entangled state, meaning that the state of one of these particles is forever linked to the state of the other particles in the same entanglement group. So if one particle changes its state, all the other particles are also affected immediately, no matter how far away these particles are in the universe. They may even be millions of miles away, and their state changes immediately, like instantly, which basically means not even at the speed of light. It's like literally instantly. Albert Einstein himself was deeply disturbed by this inexplicable paradox, which he called the spooky action at a distance. And what happened is that scientists have taken this principle of quantum mechanics and built quantum computers reflecting these principles in order to simulate the natural phenomena around us, which classical computers wouldn't have been able to simulate.
So that's fascinating. I mean, really, if you think about one of the bedrock principles of computing is, sort of the binary logic that everything's based on. And, if you have, 10 bits, you have 2 to the 10th different possibilities, or 1,000, or, et cetera, up from there. But each bit sort of operates independently. And it sounds like what you're saying is not only can each qubit exist in multiple states, but the fact that you have multiple qubits, they don't operate independently, they're entangled. So now all of a sudden, rather than that same number of bits being able to handle 1,000 different possibilities, it could do hundreds of thousands or millions or a lot more, which has to believe you can solve much more complex problems, right?
Absolutely. And this actually is something that is reflected at this point, not only when scientists want to simulate natural phenomena that can occur in physics or in chemistry, but also in other domains that are perhaps disconnected from chemistry or physics, such as finance. Pharmaceutical companies can benefit from this as well. For example, in the discovery or simulation of new drugs or new vaccines. Right now, we have reached the limit in terms of what a classical computer can do. Just to give you an idea, for example, when it comes to pharmaceutical companies, it's a topic of high importance right now because we're looking for medicines for new diseases or vaccines. What pharmaceutical companies need to do is simulate the creation of a new molecule, first on a computer, and make sure that this molecule is strong enough to stay together, and also strong enough to form a bond with this particular receptors in the body. Simulating molecules is a very expensive computation. Just to give an idea, to simulate the molecule of caffeine, which is not even a drug that we would use today for curing a disease, yet that would take a computer with a number of bits equal approximately to 10 to the power of 48. Now, the number of atoms on the Earth is 10 to the power of 49, which basically means no classical computer will ever be able to simulate such a basic molecule as caffeine. However, a quantum computer with only 160 qubits can do it. So pharmaceutical companies that build the new materials, new plastics, green fuels, new fertilizers, new batteries, but also companies in the logistics industry can benefit from better transportation routes, better sourcing of goods, handling and sortation of goods as well. And finally, we in the financial world that can benefit from quantum computing because it has high applicability to any type of optimization problem and machine learning as well.
Yeah, that's fascinating, right? Because you go from taking something using your caffeine example that's completely impractical, right? More than the number of atoms on the Earth to be able to simulate, something as simple as caffeine, down to something 160 qubits sounds much more, possible and reasonable, right? So that's got to have some pretty, remarkable ramifications for how we think about computing and sort of what's possible. Because can you talk about some of the implications of that to the industry?
At this point, the new horizons are going to become possible, things that we didn't think would be possible before. So as I mentioned, new drugs with limited side effects are going to be discoverable through the use of quantum computers. Right now, drugs are simulated on a classical computer, but unfortunately with approximations. And these approximations are those that hide potential side effects that can be even harmful to people. Now, the benefit of quantum computers can also reach the domain of a green environment, because through quantum computers, we can now discover new materials, new, more efficient batteries, new fuels, and even new fertilizers. To build the fertilizers that we use today, we consume a high percentage of natural gas. I believe it's like 2% of all the natural gas that we consume every year. It's just spent to build the new fertilizers. This is such an expensive process as well. Now, it's necessary to build new fertilizers in a more efficient way. And with quantum computers, we can do this in a matter of 24 hours. But we're talking about the quantum computers of the future. If we want to do the similar computations using classical computer, it has been estimated that a classical computer put in the position of simulating the molecule of a new fertilizer may take something like 800 years. Wow. So there is a huge difference. And this is something that we will see in the next few years.
So much more powerful simulations are possible, much more powerful modeling. It seems to me you mentioned machine learning, a topic we've covered many times on the on Tech Trends. It's got to be able to sort of really juice the kind of things you can do with machine learning, how fast models can learn, and the things like that, really to enable you to do things that we can only dream of right now, right?
That's true. For example, we know that machine learning is already like an error-prone kind of technology because there's always some false positives and false negatives when it comes to machine learning. So we need to do our best to really lower the number of false positives and false negatives. Let's take as an example fraud detection. This is a use case for a bank. You can imagine any false positive causing a credit card to be blocked without any reason, which is like really annoying for a customer. At the same time, any false negative is also problematic, even more, because it means that a fraudulent transaction has actually been authorized. So we need to be in a situation in which these become really rare exceptions. Unfortunately, fraud detection is really a hard problem because we have imbalanced data. In a sense, this is we're lucky to have imbalanced data, because what this means is that the majority of the transactions are not fraudulent, and only a small minority is a fraud. But from a machine learning perspective, this makes the learning part of the algorithms very complicated, which is what leads to false positives and false negatives. And this is where we are devising new algorithms using quantum computing for fraud detection, for example, which is one special example of machine learning.
Okay, so it almost sounds too good to be true, the kind of power that we'd be able to use, that we haven't been able to do before, we haven't been able to dream of before, right? I first heard about quantum computing in the early 1990s, and it feels like we've been talking about this forever, right? We did an episode of Tech Trends a couple of years ago with Elena Zislin talking about quantum computing. And even then we talked about, okay, this is a ways away, but it feels like we're making more progress towards this. Things are speeding up very quickly, right? So how long is it really before we start to see quantum computing much more in the mainstream?
So there are two milestones that we expect to see in the next few years. One is called the quantum advantage. Quantum advantage means that quantum computers will become more powerful and more accurate than classical computers. Right now, that's not the case. Quantum computers are there, they exist, but they're like in an infancy state. With quantum advantage, they will surpass classical computers, but classical computers will continue to be useful, and there will be like some kind of race between classical and quantum. Quantum supremacy, on the other hand, will be another milestone coming later, in which quantum computers will be able to do things and perform computations that classical computers cannot do in any reasonable amount of time, such as the simulation of caffeine. So quantum advantage is expected to happen as early as 2 or 3 years from now, and quantum supremacy at the end of this decade. So we are really excited to see this progress coming.
Yeah, that's much faster, I think, than most people realize, right? So with that in mind, that's only a few years away, a couple of years for quantum advantage, and maybe less than 10 years for quantum supremacy. How are we thinking about, and let's talk about the financial industry, and then specifically at JPMorgan, how we're thinking about the applications of quantum computing?
Absolutely. The applications of quantum computing is something that we need to think of right now, because based on what I said before, somebody could say, okay, so we still have a couple of years for quantum advantage, maybe 9 years or 8 or 9 years for quantum supremacy. So there is time to get worried about it. In reality, no, there is not so much time, because the time that we have now should already be used to become quantum ready. Meaning, this is the time, this is very precious time in which we should build algorithms that run on these small and kind of limited quantum computers that we have today. But the algorithms that we write today will be reusable tomorrow on the more powerful quantum computers. So this time is really very important. And in terms of finance, the use cases that we're looking at are all those that have prohibitive complexity, those for which we have to resort to approximations. For example, portfolio optimization is a problem with very high complexity. right now we do portfolio optimization every day in the banks, in the financial institutions in the world, but we do portfolio optimization with approximations. Eventually, we want to be able to really limit the approximations. Other problems that we really want to solve with quantum computing are option pricing, risk analysis, and machine learning. So from the point of view of quantum computing, finance is actually estimated to be the first industry sector to benefit from quantum computing, even before pharma, new materials, and transportation and logistics.
So that's fascinating, right? Obviously, there's no shortage of use cases in the financial industry. Risk management alone could keep us busy for decades, but portfolio optimization, as you said, fraud detection, lots of opportunities in the financial industry. If we look beyond the financial industry, though, and not just in large industries or with large pharma or things like that as well, what are the challenges to making quantum computing much more available to smaller companies or people that maybe don't operate in these big industries?
You're right, Anish. There are a lot of challenges, in fact, and the reason is that quantum computers, first of all, that they're not as easily manageable as classical computers. Like we have our classical computers, even our smartphones are classical computers, our laptops, and so on. So quantum computers are not that easy to manage because they are very large and they have to be kept at very cold temperatures. The problem is that quantum computers are rare, so we expect to see a race to use quantum computers by many different companies, as you said, not just the pharmaceutical companies or the financial institutions, but like every company that wants to use quantum computing will have to book some computing time, and that will become almost a bottleneck in the future. The other thing to consider is the computational power of quantum computers. So the superposition and entanglement properties that are at the foundation of quantum computing, they actually give rise to a very interesting property of quantum computing. And this property is the following: the computational power of a quantum computer doubles with every new qubit that has been added to the quantum computer itself. This is the reason why we only need 160 qubits to simulate the molecule of caffeine, as opposed to 10 to the power of 48 classical bits. Now, but from what I just said, it will look like we just need to add a few more qubits and we will be good. In reality, the number of qubits is just one side of the coin. The other side of the coin is the quality of these qubits. So what we're facing today is also a quality problem, in the sense that qubits are so sensitive and so susceptible to the environment around them that they can easily be exposed to environmental noise. In other words, they can become easily perturbated by the noise around them. And I'm not talking about the sound, but just any single interference coming from magnetic fields or temperature changes and so on. So a qubit can only keep its state of superposition up to a certain amount of time, which is usually very short. And this is called its coherence time. As soon as the coherence time is over, the qubit will lose its superposition. So we need to make sure that the entire computation that we want to perform on a quantum computer takes place before the coherence time expires. At that point, after the expiration of the coherence time, we will have decoherence errors. And then there is another problem that we need to consider. Just like in classical computing, we have circuits. We have also circuits in quantum computing. And these circuits are like a sequence of operations that are performed on the qubits. These operations are called gates. So you can imagine, given that a qubit can be any value between 0 and 1, can be 0 and 1 at the same time, the exact value, in the exact state of a qubit has to be manipulated with care, because any single operation performed by a gate has to be extremely precise. Therefore, any gate imperfection propagates through the execution of the quantum program and can lead to severe errors if these gate errors are too strong. So we are looking at quantum computers with more qubits, but also with more precise qubits. That's what it is actually going to happen in the next few years. In order for quantum advantage and quantum supremacy to take place, we need to have quantum computers with a solid number of qubits, but also with a solid quality. Otherwise, we will have imperfect computations and we will not be able to use them industrially for our daily problems.
So Marco, the first time I heard about quantum computing was in the context of security and cryptography. And one of the bedrock principles of cryptography, specifically public key cryptography, is the fact that it's based on the principle that it's very difficult to factor very large numbers. And that's one of the problems that people talk about quantum computing being able to solve, right? So that's got to have some pretty serious implications for security and cryptography across the entire internet, doesn't it? Can you talk about that a little bit?
Absolutely, Anish. This is a very good point because it actually means that quantum computing, in spite of being such a good technology that in the future will allow us to solve problems of critical importance to us, it will eventually solve problems that we didn't want it to solve, such as you said, the factorization of large numbers into prime factors. This problem is at the foundation of public and private key cryptography. And so by solving that problem, attackers will be able to infer a person's private key by knowing that person's public key. So what can we do about this? We have two strategies. One is called the post-quantum cryptography, or PQC. Post-quantum cryptography is the creation of new cryptographic algorithms that are safe based on today's knowledge of quantum computing. So no quantum algorithm has been discovered that can break these new cryptographic algorithms that don't use a factorization of large numbers as their foundation. Mm-hmm. So we need to transition to these new cryptographic algorithms because they're not yet vulnerable to quantum computing. And we need to do it as soon as possible, even now that quantum computers are not yet that powerful. We don't have so much time left. And the reason is that attackers are already taking snapshots of private communications between different parties. And even though they cannot decrypt that data now, they will be able to decrypt it later, and there will be a lot of confidential data there. And then, as I mentioned before, there is a second strategy that we're looking at from a research perspective, and this is called the quantum key distribution. This is a new cryptographic protocol that is not based on algorithms. So it's not algorithmic. And so quantum computing cannot break it because there is no algorithm there. Ironically, QKD, quantum key distribution, is based itself on the principle of quantum mechanics. So it's almost like fighting fire with fire. Because quantum key distribution is resistant to quantum computing, and it allows two parties to exchange the same key without having to use public key encryption.
So that makes sense, because in theory, if you're using quantum computing to break cryptography, you should be able to use quantum computing to build even stronger security mechanisms, right? The problem with that, though, is that quantum computing isn't powerful enough yet today to be able to do some of those things. That could be 5 or 10 years from now, but we don't have that long because of the issue you mentioned about data being copied today for decryption in the future, right? So you're leveraging these classical computing-based post-quantum cryptography algorithms to basically fill that gap. So in the short term, for the next 5 or 10 years, we use post-quantum cryptography to secure this data, while long-term, you have this issue once the power is there and other things to use quantum key distribution. Is that right?
Yes, and I have to say, this is actually a very challenging process. Even transitioning from today's cryptographic algorithms to the new post-quantum cryptography algorithms is not like an easy task because it requires having the knowledge of all, for a company, for example, the company has to have the knowledge of all the vulnerable points in which public key encryption is used. And this can be in the software, in the hardware, in the network infrastructure. So all these vulnerable points have to be identified. A company has to also interact with the vendors. For example, the vendors that provide the email program, the cloud infrastructure, everything has to transition to the new safe cryptographic algorithms.
Yeah, so that's a great point, and it's going to keep the security industry busy for decades to come, I think, around that as well. So Marco, let's say we were to have you on Tech Trends a year from now. Where's quantum computing going to be?
Given the pace with which quantum computing is evolving, maybe a year from now, we will already be talking about quantum advantage. If not, for sure, we will have more qubits, less error, longer coherence, more fidelity in the basic operations, the gates that we mentioned before. So we will definitely be closer to quantum advantage. Also, you know that at JPMorgan Chase, for example, as well as many other companies, the research is really happening at the level of algorithms and applications. There are companies that are really focusing on the hardware. We are hardware users, but we're not performing research at the hardware level. So if we look at the algorithms and the applications, we expect to see a lot of progress. So a year from now, we will probably be talking about new disruptive algorithms that can really signify a lot of new discoveries in many different domains. And finally, I expect to see more progress in the area of post-quantum cryptography and quantum key distribution.
So finally, Marco, what advice would you have for any of our listeners who want to understand what they can do with quantum computing or learn more about how it applies to them?
This is actually a very important question, Anish. Thank you for asking it, because I think this is the time in which, as I mentioned before, companies have to become quantum ready. So this is the time to learn quantum computing. So companies should actually start building a team internally that understands quantum computing. They should start educating the rest of their firms to let everybody understand what quantum computing can do, so that then the different teams can then rely on the central quantum computing team for devising new algorithms and new applications. It's also important to realize that a lot of the work that has been done so far in quantum computing has been really scientific. You know, new algorithms, new papers, maybe small prototypes. And these prototypes maybe are like scattered in some repositories here and there. It's time to transition the science into business. It's time to really be serious about organizing the quantum algorithms and these prototypes into solid pieces of code, the solid programs, organized also according to the most important principles of software engineering, so that algorithms can be reused, just like we do with the classical computing. So it's time to transition from science into business. That's what I would like to recommend to companies in terms of quantum computing today.
So even though quantum computing might be a number of years away for most companies, right? It's never too early to learn more about it, understand how it might be applicable to your environment, start building a little bit more capability and knowledge around the field, but also thinking about what are those problems that you always thought were too hard to solve. And the one thing I'd add to what you said, Marco, is start thinking big. Think about how your business might be different if you could solve those previously intractable problems. And at the same time, think about, as you mentioned, think about all those places where you might have security issues that you need to address going forward.
That's right, Anish.
Well, Marco, this is a fascinating topic. Thanks very much for joining us and sharing your insights and taking something that is so complex and making it more understandable for folks.
Thank you, Anish. Thank you for having me. Anytime.
And to all of our listeners, remember, if you enjoyed this episode, you can rate us on a Spotify, Apple Podcasts, or wherever you get your podcasts. Tune in next time.
you.